Great. So here we are. This is the Monolith platform. Now, the Monolith platform uses notebooks and dashboards. It's a little bit similar to Jupyter Notebooks in that respect, if you've seen that before. But in this case today, I'm just showing you dashboards. We'll go right into it. So in this particular dashboard, we are predicting the next test using AI. So take test 1, predict test 2. We've got the first data set used for AI modeling here. This is it. This is the data set itself. You can see it looks like an Excel table or a CSV table. There's a couple of different parameters that we have here. We've got current density, we've got cell voltage, we've got pressure, relative humidity, and we have quite a few number of rows. We've got 1,000, roughly 1,250 rows roughly, and a couple of columns. And what we're going to do is we're going to train an AI model to take current density and pressure and relative humidity as inputs, and we're going to make it predict cell voltage as an output. So those are the inputs, and this will be the output. And so I scroll down, and here we are. Here we've done it. So we actually have a curve prediction here, which comes from a model, and this is not historical data. This is not just the data that I've shown you here visualized. No, what we're doing here is that we've trained an AI model on, in this case, it's a neural network, and then on this data set from test 1, and it has produced a new prediction for this. I can change my inputs and I will get a new prediction. So I can change this slider here, for example, the spinner will roll and I'll get a new curve prediction shortly thereafter. While we wait for that new curve to come, this will update soon. We will see that we have a bright line, which is the curve itself, and the prediction itself. And then we also have a shaded area, which is you see the curve just updated, which is the uncertainty interval, which is a 95% confidence interval across the model prediction. So what have we done so far? We've taken data from the first test, we've trained an AI model, and we've now got a curve prediction from it. Now, in this case, this particular prediction, it is what we're going to use to make a prediction about the second test. So we've got test 1, trained a model. We're going to use that model to predict test 2. So test 2 is over here. And of course, in our context, I've said that we have the data set available because we've actually done the second test. But in the real world implementation, you might not have this data set available. You wouldn't have the results available. What you would know is what your conditions for the inputs are. So you would know what you would like to run as current density or pressure or relative humidity, simply because you know what you want to run your test as, right? You know what your conditions will be, you know what to set them at, and it's up to you to decide. You as a test engineer have to decide what different ranges of my different parameters do I want to cover in this next test, and you will have specified these ones yourself. Now, what you won't have is the cell voltage, which is the output, which is the result of the test. I have it here because we've done this test. It's just 15 rows, but we're going to take the model from test 1, use it to predict test 2. It's important to emphasize that the model has never seen test 2 before. The model was not trained on test 2. So we'll see how well it does, and I can compare the actually measured results against the prediction that we would have had if we had not performed the test at all. The second test, that is. So that's what we'll look at now. I'll scroll down. Here we have the validation plot of the trained model predicting the unseen second test data. So you can see that we have the bright red line, which is the prediction itself, the uncertainty interval in the form of the shaded area, and we've got the white dots, which are the measured values of the second test. Now, the model does reasonably well in matching the measured values up until about here, but then you can see that at those higher current densities from 1,500 onwards begins to deviate a little bit and quite a lot at the last data point. We'll talk about that more later. So to summarize, we have taken a model that was trained on data from test 1, and we've applied it to unseen data in test 2, and we've gotten a prediction, which is reasonable, for test 2. Now we'll go to the second step, which is understanding test performance better with AI. So here we have another data set to start with. This is, again, test data. We always start with data. In this case, we've got a slightly different data set. It's slightly shorter. It's got 651 rows, and it has additional columns than compared to the one that we saw earlier. So we've got membrane compression, and we also have membrane water uptake as columns available. In addition, we also have the relative humidity and the pressure that we had before, and then the cell voltage and the current density. So we're going to train an AI model on those columns now as well. And we'll use that to better understand, like a digital twin, the system that is underneath, in this case, our membrane electrode assembly. So I'll scroll down, and here we have our new AI model. Again, you can see that we have multiple inputs that we can vary. And I might take this slider, I might shift it here. You'll see that the spinner appears while that's turning. We'll wait for a new curve prediction to appear. But the same principle as we saw before. In addition to predicting just a curve, you could also have predicted a surface or a full data set. There we go, it updated and the curve was slightly changed. So what can we do with this? Well, we can interrogate this in reverse. Like I said, if this becomes a sufficiently accurate digital twin of your system, then you might want to understand, how do my different inputs, pressure, relative humidity, membrane compression, membrane water uptake, current density, affect my output, which I care about, which is the cell voltage. And we can do that in one of the ways on the platform using the explainable AI algorithm that we have in one of our steps. So I'll show you what that looks like. So we can apply the explainable AI algorithm globally across this model. I told you earlier that the model was trained on about 650 rows of data, 650 data points. So the explainable AI algorithm, when it's applied globally, will be applied across all those training points, all those 650, and we'll get a result from it, which is sort of averaged across that. That's what it's going to look like. So what we can see here is that we have a relative ranking of the inputs in their value, in their contribution to the output. So we can see that current density has the most contribution to a prediction of cell voltage, but then followed by membrane compression and pressure and things like that. Now, why is this useful? This is useful as a sanity check, first of all. If you're a subject matter expert in your domain, if you're a fuel cell test engineer, then you would like to look at this and see that this ranking matches globally what you would expect your system to behave like. And it should raise a flag, it should raise a red flag for you as an engineer if this ranking was different from what you expected, right? The current density quite obviously should be the most contributing to cell voltage performance in the fuel cell. And if it wasn't, that might indicate that you might have made a mistake in the setting up of your model. Maybe you've picked the wrong inputs or outputs along the way in some step. Maybe you've introduced some errors in your earlier calculations or your transformation of data. Maybe you've got data leakage happening somewhere. So this can be a valuable step to explore whether the model that you've trained seems to be capturing the physics as you would expect it to be in your system, if these relationships seem appropriate or not. So that can be a good sanity check to start with, to give you some structural checks on whether the structure, at least, of your model seems to be robust. And if it is, and if we can proceed from there, then we can perhaps interrogate this model further to give us a little bit more detail. So we might go one step further and apply this explainable AI algorithm locally to just one set of conditions for our system. So this is what that might look like. So when I apply it locally to just one set of conditions, I can specify those conditions here with my sliders. You see I've specified them here. I can get a similar plot, again, with relative impact of the different inputs to the output, but I get a color as well. The color gives us a direction. So the green inputs mean that an increase in this input leads to an increase in the output as well. And a red input means that an increase in this input leads to a decrease in the output, which in this case would make sense based on what these polarization curves look like. Now, I might change one of these values. Maybe I'll change pressure to go up a little bit like this. You'll see a spinner. As we recalculate, we apply the algorithm to the model. And what you can see is that as a result of me changing the pressure up higher, I believe it's going to change the relative ranking of pressure in that particular point, which could be valuable, as you can see. So I've increased the pressure for the point that I'm exploring in my design space, keeping in mind that all of these variables here with this setting just represent one point in the design space of my fuel cell's performance. And at this particular point, it seems like pressure actually has a higher impact on the eventual cell voltage than it did earlier, and it bumped up other inputs in its ranking. And that might be valuable for me to know if I want to explore local behavior of my system using this model, as opposed to having to explore it in some form of way of testing. Right. That concludes everything I wanted to show for explainable AI and for the understanding of test performance. Yusuf, back to you.